Repeated measures. This stuff is important. Again, as we talked about before, these repeated measures designs are incredibly powerful. If you can at all incorporate a repeated measures component into your analyses, it's in your best interest to do so. This is just going to make your overall analysis much more sensitive to the types of things that you might be interested in teasing out. Sometimes you can't, but if you can, it's definitely worth it. The problem is things get a little bit tricky in terms of when we get within subjects, and then particularly if we add between, want to make sure that you got a good handle on what's going on. But I'm going to start out with a review, okay? And again, we went over this in ANOVA, so this is all going to be a review from this semester too. We're thinking about our ANOVA analysis of variance. Again, what we're doing here, remember, we're looking at to test differences across 2 or more different populations, right? We can't test the populations, but we can grab samples from these different populations. These populations can be different pre-existing groups, or it could be something that I create, right? I administer some sort of experimental manipulation to Sam. Sam is now part of a new population that had never existed before. Sam's part of the population that's received this manipulation, right? And so we want to see if Sam is different than Stephanie, who got a different manipulation and is part of a holding population that has only ever experienced that manipulation, right? And so what we want to do is see whether or not the samples that we draw from these hypothetical populations are reliably different, right? And so we're always going to see differences in these samples, right? The average score of our individual samples are always going to be different to some extent, right? Unless we've got really rough scoring. We're always going to see some difference. Question is what's accounting for these differences, right? Are these differences a product of just random fluctuations, just random stuff, or are the differences driven by true differences within these populations on whatever outcome it is that we're looking at? So our hypotheses here, right? Our null hypothesis is the mean of group 1 is equal to the mean of group 2 is equal to the mean of group 3, and we're talking about our populations here, right? We can talk about this as there's no relation between x and y, right? Sam, in this example, what's x and what's y in a hypothetical universe? What's x? Y is y. What's x? Well, dependent variable will be y. What's x? Well, that's what we're looking for, right? This can start to get tricky. Our x is our category, whatever our categorical variable is, right? So our x could be condition, right? It could be major. It could be anything, right? And so again, from a means-based analysis, right? This is a hard thing to get our heads off of. One of the things that showed up on the exam, people talking about sort of taking the simple slopes and then to create a graph at high levels and low levels, and you started talking about things in terms of differences in expected values, which sort of gets off track of the whole idea with continuous regression models, right? We're not looking at differences in expected values, we're looking at relations over time, right? So we can talk about our one-way ANOVA as differences across groups, but we could also talk about it as a relation between my grouping variable and my outcome. Right? So if I'm looking at differences in salary or credit hours or whatever across psychology majors, engineering majors, and kinesiology majors, I can talk about that in terms of groups differences, but I can also just say what's the relation of major to credit hours, right? That ends up being a much more flexible approach to going through and thinking about things. So we could say the means are equal, or we can just say there's no relation between whatever our grouping variable is in our outcome. Okay. So, but this is tricky, right? Because like people will say, well, my variable is psychology, kinesiology, and engineering. Nope. Those are levels of your categorical variable. Your construct is major, right? And these are just representative categories of that, right? So one, to keep that in mind. So our alternate hypotheses here, at least one population mean differs from the others. Data are unlikely, assuming equal population means this is actually, I mean, remember if we go way back to some of those Cohen articles, right, and interpretation of null effects, right? Again, our whole method is predicated on this idea that assuming the null hypotheses, assuming that there are no differences in average credit hours across majors, it would be unlikely for us to have obtained these means. Now there's problems and interpretations of that, but always important to think about when you're trying to interpret null effects, saying what does this mean, okay? Our F-test here, we're looking at the variance between sample means over the variance expected if the null hypotheses were true, okay? So here, what we're trying to do with our ANOVA models is partition things into systematic groups and variability that's just due to error. And this is going to be our between groups and our within group stuff. Remember, if we're talking about between group differences, right? Between group differences in this little table that we've used before, what we're looking for is why the means across these four groups are different, right? It could be due to systematic differences, due to just the effect of, looks like temperature on number of problems solved, or we could have just not random differences due to just random individual differences across the people who got categorized in this stuff. We could have things like experimental error, right? Maybe every time we ran this group, someone was beating on like ceilings or ducts or something and was distracting, right? This is the stuff that we don't know about, right? And so what we do to look at our between group differences, we're looking at variability across the group-based scores, right? And again, we're looking at variability. Why do we use variability, Alex, instead of just looking at mean differences in ANOVA?
Why do we look at variabilities?
Yeah.
Because it allows for you to recognize more effects, recognize individual differences for them.
Yeah, what's going on in ANOVA that makes mean differences hard? Or just pairwise differences? How many groups do we have? All right. If we've got 3, 4, something like that, it's hard to say, all right, this is the overall differences we see across groups if we're stuck with pairwise comparisons, right? So what we do is we use variability. Variability is our proxy for differences. So Katie, if we have lots of variability, what does that mean?
There's lots of variability
In these scores?
probably systematic.
Right, probably a systematic difference, but at least it's telling us there's lots of, we're seeing quite a bit of difference between these scores. And if we have small variability, everybody's about the same, right? And so when we think about this in terms of variability, we've sort of been harping on this for a couple semesters now. If I see a set of scores, or I see a set of means, and the variability across those sets of means is very low, then it means there's not a lot of differences right there, right? But if we do see high variability, right? If we do see a lot of differences or high variability, that's saying that sort of our means are kind of all over the place, suggesting to us that we have more differences across our scores. And this is a kind of a crucial thing to keep in mind as we're going through and working through these ANOVA types of approaches. Variability is code word for differences, right? If we're seeing lots of variability, it's just we're getting a lot of differences across whatever we're measuring. If we have low levels of variability, it just means everything's kind of uniform, everything's kind of falling on top of one another. Okay. So this is our between group differences. In this example here, we're looking at differences across group means. Right? By contrast, our within group differences. Right? Again, remember that if our manipulation or our grouping variable, whatever our independent variable is, if that's the only thing that's driving outcome, Morgan, what should all scores within a given group be? They should be identical, right? If temperature is the only thing that determines what people's performance on this task, then we would expect everybody who's got in the 50%, or excuse me, the 50-degree room they're identical, right? And everybody in the 70 degree, identical. Everybody in the 90 degree, identical, right? But as soon as we don't have that, if there are other things going on that we're not accounting for, if there's things in the model that we're not accounting for, what do we call that, Stephanie? Error, yeah, right? And so we're seeing within our ANOVA design, we're seeing differences within each one of these groups, right? And those differences tell us that there's other stuff going on that's driving performance that we're not accounting for, right? And so if we're not accounting for it, it's error. And so we can have individual differences, experimental error, all sorts of different stuff that can go through and start to drive this within group variability, right? And so what we've got with our F ratio when we're working with ANOVA, we've got our between treatment variance over our within treatment variance, right? And we get this as our observed group differences over differences that we would expect given the null hypotheses, right? And so if we think about this, right, our within treatment variance is the differences that we're seeing across scores of between individuals within a given group, right? If the only thing that's driving differences in the means across our groups is the same thing that's driving differences in the scores within a group, then we would expect this F ratio to be 1-ish, right? The differences that we're seeing here across groups is no different than the stuff that we're seeing within groups. It means there's nothing to see here, right? We don't have strong evidence that there's any systematic differences across these populations. But if we see that the differences we're noticing across groups, across those group means, is quite a bit greater than the differences that we're seeing on average within means or within groups, then that's starting to say there's something systematically different about these populations, right? Whether they're pre-existing populations, whether they're populations we've created through some experimental manipulation or some type of treatment, right? If these differences are a lot more than these differences, then we're going to start to get an F ratio that's going to get larger. We're going to see have more evidence that there's something actually going on. And again, if you think about this as in the numerator, if we're catching systematic effects and random differences, we divide that by random differences. We've got a good number of systematic effects. These two things are going to cancel out, and we're going to end up with something quite large, right? But if we, or at least bigger than one, but if these systematic effects are quite small, close to zero, well, if we cancel the random differences out of the numerator and the denominator, all we're left over with is just sort of our no effect to begin with, right? And so thinking about these ratios, what they mean, is going to be really, really helpful when you're trying to tease apart what's going on with the different effect sizes that we're going to be calculating and trying to understand the analysis we're going to run with repeated measures designs. So again, our two scenarios here, right? We've got systematic, or we've got no systematic group differences. The differences we're seeing between group means is all attributable to random error, right? Then we're going to have no systematic differences plus random differences or random differences. We're going to get an F value of about 1, right? But if we were layering in addition to the random differences, because we're always going to get random differences across our groups, right? There's going to be error across our groups due to sampling stuff and all sorts of different types of factors. But if we've got a strong signal, think about these systematic effects as a signal, right? If we've got a strong signal that's going to go through and rise above and beyond our random differences here, and we're going to get an F ratio that starts to get larger, closer to something that we can use, at least within the system that of our inferential statistics make a claim that it looks like there is something going on here. Okay. Questions about this? Okay. So, again, want to do when we, and this starts to become really important because the analyses and the output that you get for your repeated measures designs, and particularly your mixed ANOVA designs where you have within between, you're going to have to know where variability is coming from, what it represents, and things along these lines. And so if we're talking about our ANOVA designs, our sum of squares total, this is our total variability in our set, right? So this is the sum of the squared deviations of every participant's score from the grand mean, okay? We square that deviation, add all those together, that's our total sums of squares, right? So if we go through and take every score that we've, in our entire set, and subtract it from 2 and square that, that's going to give us our sum of squares total. That's the total piece of the pie we're working with. This is all the variability in the sample. This is all the variability that we're trying to come up with, or trying to account for. Okay. Our sum of squares error. This is the variability we're seeing within each condition or group. This is going to be variability within individual conditions due to individual differences, error, things along those lines. If we're thinking about the calculation of that, this is everybody's, or within a group, each member's score, the deviation of that from the group mean, and the square of those deviations, right? So we're just taking 0 minus 1, 1 minus 1, 3 minus 1, 1 minus 1, 0 minus 1, taking those deviation scores, squaring those up, adding those up, and then doing the same thing for treatment 2, for treatment 3. This is giving us a total variability of within group variability in our data set. Okay, and this is sum of squares error, right? This is what's going to go in the denominator of our F ratio. Now the issue is, and just to complicate this, homogeneity and variance starts to become really important when we're calculating individual effects, when we're calculating effect sizes, things along those lines. Because if I have in treatment 1, everybody's all kind of the same, but in treatment 2, I have a lot of variability there, right? What I end up having is much more variability here, or excuse me, here than I have here. And I may have violated a homogeneity and variance assumption, right? And so if I just start pulling my sum of squares error for different types of things, I might be overestimating the amount of error that's actually in the groups that I'm interested in, right? If I want to take a look at, so if I have little within group variability in treatment 1 and 3, but then 2 is all over the place, right? My sum of squares error is going to be the average of my within group error across my conditions. But if this is a whole lot higher, what has that done to my error term? Made it big, right? And if I'm just trying to compare groups 1 and 2, and this is the term I'm using in terms of a standardizer or an error or something like that, I'm saying there's a lot more, I'm saying that there's much more error, within group error in these two groups than there is, because treatment 2 is sort of way out of bounds in terms of stuff, right? So these are the practical reasons why we want to go through and take a look at those violations and make sure that we're accounting for this type of stuff. And then particularly too, think about this, not only violations of homogeneity and variance, but also imbalanced design, right? So I've got 10 people here, and 30 people here, right? 30 people here, that's going to weight much more heavily in my overall sum of squares than these two, right? And so now I've got a huge inflation of my estimated error, because this sample, the sample with the most error, also has the most people, right? And so that's going to be problematic. Same thing if we switch it around. Say I've got a lot of error here, but I've got 10 people here and 40 and 40. My overall error term is going to be probably smaller than I would expect had I had equal balanced design, right? So wanting to think about the impact of some of this stuff. Right? And then our sum of squares treatment. This is going to be the variability or differences across our groups. This is going to be assuming a balanced design. The number of people per cell times the sum of our group mean minus the grand mean and the sum of those square deviations, right? This formula changes a little bit if we don't have equal people or equal cell sizes, but thinking about in a very real sense that this being the difference in our group mean, or the deviation of our group means from our grand mean here. And if we see big differences in our group means from our overall mean, suggesting a lot of differences across groups, right? If we don't see much of a difference, if all of these means were stacked right around 2, not a lot of between group variability suggests there's not much differences going on between our groups. Okay. So these are our sums of squares. Our mean squares. What is a mean squared estimate? Maureen, do you remember what mean squared is? Fancy word for it? Yep, variance, right? It's just a variance estimate. Same variance estimate that you would calculate by, here's a variable, I'm going to calculate the variance, take the square root of that, get the standard deviation. Mean squared is just variance, right? And so when you're looking at your ANOVA table and you see a mean squared, that's just the variance of something, right? It's just called mean square. Sums of squares, same. Sums of squares are a metric of variability, but mean squared is actually a variance estimate. And this becomes important because in certain situations, if we haven't violated assumptions, we need that mean squared, particularly mean squared error, and if we want a standard deviation for a standardizer, what can we do? Take the square root of that variance estimate, right? And then we've got it, right? So wanting to know what these pieces and parts are, how they relate to one another, so you can go through and use some of this stuff flexibly. Questions on any of this? People kind of clicking, falling back into this. It's easier to learn it the second time around, but okay. And then our F-test is our mean squared treatment over mean squared error. So this is our simple ANOVA table. We've got our sum of squares of treatment, right? So this is giving us an index of the variability across our group means. Our sum of squares error, our sum of squares within. This is a variability, average variability within each one of our groups. Sum of squares total. This is the total variability that we're attempting to account for in our design. Our degrees of freedom, if we take our sum of squares divided by our degrees of freedom, we get our mean squared. So this is literally the variance across our group means. This is the average variance within groups, right? We take our mean squared treatment divided by our mean squared error, gives us our F-test, right? Here's our hypotheses, and so we might say if we wanted to take like a classical approach, we'd probably sort of do something with p-values in here now, right? But we would say that this falls outside of our critical region, rejecting all hypotheses, right? So on and so forth. You guys, you know all that side of the kind of stuff, right? Okay. That was a crash course on one-way ANOVA and partitioning variability and things like that. People comfortable with this? All right. So that's our between group stuff. Want to go through before we jump into our repeated measures and stuff. Want to talk about repeated measures stuff, right? Repeated measures. Remember, we're looking at the same group of people on one or more variables across two or more occasions. Why do I have an asterisk on that? Lauren, do you remember? Kind of getting there. Angela, you have an idea?
Because it should be 3. We're just going 2 before. I mean, like it can be.
Can be 2. What do you think, Sam? There we go. The matched pairs, right? So if we have a matched paired design, right, where we've matched people up for things, right, we would still analyze those data even though they're not the same people, measured across multiple occasions. If I get a clone of Stephanie and Katie and Morgan and Angela and Alex and Lauren and Sam, and I get people who are your doppelgangers on all relevant characteristics, even if I sample you all and then compare you to the next cohort that's going to come in and be exactly like you in every way except probably not as good. Right? We could use that as a matched design, right? We would go through and test that as a repeated pair. So Sam and fake Sam would be compared, Lauren and fake Lauren would be compared, so on and so forth. Okay. So benefits of these, a lot of the types of things that we're looking at, right? A lot of the phenomena that we're interested in looking at kind of is responsive to these types of designs, right? If I'm looking at what types of things improve cognition or attention or change people's response to different evidence provided in a jury, or if we can help sort of older adults remember to take their medications or things along these lines, right? Let's do this and measure you right now and then do something to you and then measure you again and see if we have a difference there. It's more efficient use of our resources. Basically, instead of when we're looking at 2 time points, we cut this in half, right? Instead of having to collect this sample under this condition and this sample under this condition, this sample under this condition, let's just collect one sample, give them all 3 conditions, and it makes things much more easy. What we're doing here is we're accounting for random error in a much more effective way, right? We're basically parceling out individual differences here. If I look at Morgan's reactions today versus Morgan's reactions tomorrow, those are going to be much more tightly connected than if I look at Morgan's reactions today and Stephanie's reactions that day, some other type of thing. What we're actually doing is we're modeling out and pulling out those individual differences to make a much stronger design. Now, limitations, we can't always do things in a repeated measures design. Sometimes we have carryover effects that we don't want, right? So if I want to see people's reactions to sort of playing a joke on them to get fear, anxiety, or humor, stuff like that, if I show it to you again, you already sort of know what's going to happen, right? So that's not a reasonable thing to do. We can't use a repeated measures design there. We also end up with some additional model assumptions that we have to be sort of aware of if we are using our repeated measures designs. These can start to get relatively complex because you, instead of just looking at things within between, we're sort of pulling things out in a number of different areas, and as your design starts to get increasingly complex, your analysis starts to get increasingly complex, so there's cost with this. But if you're comfortable and competent in using these things, it can be a nice way to go through, particularly when you're designing studies for thesis, dissertation, experimental work, and things along those lines, right? So important to keep this in mind. So paired sample T. Oh yeah, what's up?
I have a question.
Yeah.
So if you have a high rate of participant dropout, could you have a partial match paired design for the people who dropped out, or would that introduce too much error?
That's tricky. What's that?
I was asking for a friend.
Yeah. I probably, like if I was reviewing that paper, I'd think, I don't know about that. But the nice thing is if I'm measuring something. So in my dissertation, what I was doing is I was looking at some physiological sub-skin conductance, right? And sometimes we would get someone where we had got the first measure and then someone would fool around or sort of do something and break the connection, then we lose that data, right? For the second and the third time point, right? So basically we've got a problem there. But what we know about skin, anybody worked with physiological data before? Okay. What happens is the correlation of physiological data across multiple time points. If you measure my skin conductance right now and you measure my skin conductance 2 minutes from now, what's the correlation between those two readings going to be? Through the roof,
Yeah.
right? And so like correlated upwards of 0.9 with one another, right? And so in that case, I didn't have too much of stuff, so I just imputed data so that I wasn't starting to lose stuff, right? And this is good if you've got across time 1, time 2, time 3, and the correlation across your repeated measures are really high, you're in a pretty good spot to be able to recover some of that stuff, as long as you've got an initial score somewhere in there. Now, if you lose all of it, then you're kind of screwed, right? But let's say I've got a sample of 50 people, and I know that on average, my correlations between my assessment points, whether they're self-report measures or any other thing, is 0.7, 0.8, something like that. As long as I don't have a whole lot of people out there, I could probably make a pretty good argument for using some sort of imputation technique for saying, all right, well, this is the proportion of data that was missing. However, what we did is we ran an expectation maximization program and went through and sort of estimated values for these cases where they should be, right? It's a tricky thing, right? And I would go back to that switch on and off the article, but you're much better off there than if, let's say I've got a twin subjects design and half of my people don't have, didn't report their sex. That's a hard thing to recover, right? Because like, what is my good predictor of gender that I have in my data set that I'm going to use to determine who that person was, right? So in that situation, that would be something I would look at instead of trying to, well, this person is also 70 and sort of living in this place, and so I'm going to go through and just measure their responses there. You're still going to get a lot of individual differences on that. Okay. So with matched pair stuff, what you typically would want is basically we want to figure out what types of compounds could we have, or what types of things are causing static. So I'm going to match people on age, gender, personality, sort of, if it's a clinical study, diagnostic status, like all these types of things to go through. We don't see a lot of these designs because it's oftentimes just easier to capture people on a couple of different occasions. Does that help? Yeah. Cool. All right. Any other questions on this stuff? All right. So our paired sample T, right? This is going to be important. You're going to need to know your paired sample T because a lot of what we're going to do is going to come down to paired sample T. Luckily, you know and are familiar with your paired sample T. Paired sample T test used to examine changes in scores within individuals across repeated assessments. Again, and such a crucial piece of this, remember that when we're calculating our paired sample T test, our difference scores are primary unit of analysis, right? At the end of the day, my hypothesis is the mean of my difference score is equal to 0, or the mean of my difference score is not equal to 0, right? In general, the question we're asking here is what is the mean difference score in the population, right? Now, what we do with these repeated measures is we go through, and in SPSS we go down through, we see we want a paired sample T test and go through and say, here's the first time point, here's the second time point, it goes through and runs my paired sample T test. But I can also just go through and take my first observation, subtract my second observation, calculate the mean of my T score, and then just run one sample T test of whether or not that mean difference score is equal to 0, right? So again, what we're looking at, and our question is this the mean of the difference score equal to 0? Okay. Do these different scores deviate sufficiently from 0, include non-zero difference in the population? And this starts to become important, again, remembering that all we're doing with a paired sample T test is it's just a one sample test of the different scores is different than 0, right? That's all we're doing with this stuff. Nothing actually crazy or fancy going on with our paired sample T. So remember, to calculate our paired sample T, we've got the mean of the difference minus our assumed value under the null. Lauren, what's our assumed value under the null? 0, right? So this is just our mean of our difference score over our standard error, the mean difference. Standard error, the mean difference is just the standard deviation of our difference scores over the square root of our sample size, right? We plug that in here. And so, again, this is capturing the variability we would expect if the null hypotheses were true. In the population, if there is no difference between time 1 and times 2, if that difference score is 0, we're not going to get exactly a difference of 0. We're going to have some play and some variability in that. That's what our standard error here is capturing. So, again, question from a hypothesis standpoint, we could phrase this as the probability, or wondering what the probability of obtaining a set of difference scores with a mean of 3.5, assuming that the null hypothesis is true, right? So this is the stuff that we get, and so we're might be interested in taking a look at. That's actually not the case, right? If we're screening, the difference score is what we should be screening, right? Because that's what we're actually interested in. Here's the mean of our difference score. We want to know that that difference score is equal to 0, right? And so this is sort of the nuts and bolts of our paired sample T test with what we've got going on here. Okay. Questions about this? People kind of remembering sort of our paired sample T, what's going on? People, is anybody not clear on, so when I say paired sample T test is just the same thing as a single sample T comparing our mean of difference score to 0? People comfortable with that? Okay. Because again, I could go through and calculate the same p-value that I get here by, again, taking that mean, setting it equal to 0, and then just using this to calculate a standard error like we would in a single sample T test and just run that, right? I don't actually need these scores. This is the only thing that I need in order to calculate those data. So, all right, that was kind of breakneck speed running through everything, but all of this accumulating into this idea of our repeated measures ANOVA, okay? So now, and we're thinking about our between subjects designs, right? And so thinking about like a one-way ANOVA model, right? We're assuming that our cells are independent, uncorrelated with one another, right? So if I go through and I look at the average height of freshmen and sophomores and juniors and seniors in high school, okay? I'm assuming that no one's height in my freshman group is impacting anybody's height in the sophomore group, right? These are completely different. I also expect no one's height in my freshman cohort to be correlated with anybody's height in the senior cohort, right? Everything's independent, everything's separate from one another, right? And so what we're assuming here is that because we've got different people doing different treatments, everybody's separate, everybody's their own person, that the correlation of scores between treatments are going to be expected to be zero, right? So scores aren't going to be correlated with one another because they're completely different people in completely different places doing completely different things, right? But if we, instead of having sort of individual people in treatment 1, 2, and 3, if we have just the same group of people completing treatments 1, 2, and 3, in this scenario, we expect these scores to be correlated, right? Because if I have Angeline, instead of taking Angeline's data in treatment 1 and Alex's treatment data in treatment 2 and comparing those things, right? If I want to take Angeline's score in treatment 1 and then have Angeline complete treatment 2 and then have Angeline complete treatment 3, I'm expecting her values across those treatments are going to be related at least in some level. Depending on what the treatment is, those correlations could be quite high, right? Same thing, Morgan is here, Stephanie is here, Sam is here, right? As if I have the same person going through and completing different things, I'm expecting their scores to be correlated with one another, right? And typically this is problematic, right? Typically with our between subjects groups, we don't want our cells, our conditions, our values to be correlated with one another. But with our repeated measures designs, what we're going to do is we're going to say, all right, we already know they're going to be correlated because that's how we're collecting the data. But what we can do is we can capitalize on this. We know what's going on. We can model it and actually strengthen the power of our tests in many ways by taking that correlation and pulling it out, right? We're taking that, basically we're accounting for individual differences, right? Because say Katie's a really mean person and Alex is a really nice person. Alex fills out self-report measures really nice, and Katie's really mean when she goes through and does that. But if we go through and we have you fill out multiple measures across multiple time points, I can go through and account for, well, Katie's measures, scores on this higher, just a little bit higher than Alex's scores because Katie's kind of mean. And Alex's scores are lower than the average person on this because Alex is just kind of nice. We can go through and cut that out if we've got repeated measures and we model that, and then all of a sudden, instead of that being error that's just lumped into our denominator, we can section that out, and all of a sudden we have a much, much better test or much more precise test of subtle differences across measures. Okay. So, what's that? Not that you're mean, I think you're very nice.
I said it's true.
I've heard talk. I've heard some things. Right? Okay. So if we go through and we take a look at this table here, okay, we've got, and you can take a look and you can say if this is group A, group B, group C. Okay. What we're seeing here from a between treatment standpoint, right? For between subjects ANOVA, we've got a lot of variability within each group, right? We've got a ton of variability across these scores within our group. And so Sam, what does that, in a between ANOVA design, what does this suggest to us?
Yeah.
seeing is I'm seeing a lot of variability in Group A. I'm seeing a lot of variability in Group B, a lot of variability in Group C. What do we call within group variability? Error, right? I've got a ton of error going on here, and I'm actually not seeing that much of a difference across my group means, right? And so from a between groups design, if this was Group A, Group B, Group C, what I'm seeing is a whole lot of within group variability and not a lot of between group variability, right? And if this is the scenario I'm faced with, what am I going to say, Stephanie? Yeah, then I'm probably not going to reject it, no, right? I don't have much of a signal here, right? The variability I'm seeing among people who are all receiving the same treatment is really huge, right? And so the variability within my cells is a lot bigger than the variability I'm seeing across my treatment means, and so I'm probably going to fail to reject the null, right? I'm not going to catch a signal with this, right? But if we go through and we take a look and see what's kind of going on with this, we see that if we were to take a look at this from a repeated measure standpoint, let's say that instead of, this is my 4 people in Group A, my 4 people in Group B, 4 people in Group C, right? So I've got 12 people in my design, 4 people each cell, okay? Well, what if I say instead of a between groups design, this is a repeated measures design, right? And I say I've actually only got 4 people in this study. But if I go through and I take a look at, so person 1 is scores in treatment A, B, and C. In treatment 2, person 2, A, B, and C. 3, A, B, and C. What do we see in here, Morgan?
Treatment appears to be having some sort of effect or differences in
Right. Even though we have a lot of variability, there's a lot of individual differences across our participants, the response to the treatment is pretty uniform, right? So it doesn't matter if we're starting at a score of 2 or a score of 30. Across these repeated measures, we're seeing systematic change all in the same direction, all about in the same way across these individual scores, right? And so in this situation, if we're running a between subjects, things look pretty gross, right? But if we go through and we conceptualize these scores as a within subjects, now all of a sudden, we're seeing that on average, people are systematically getting better across these individual time points, all in the same way, right? And so what we're doing with our repeated measures design, right? We're parceling out our individual differences. So all the individual differences that we're seeing across people, like where they start, we're taking that and we're just sucking that out. That's just a whole bunch of error, right? We're going to take this out, and so what this is going to do, it's going to reduce our noise. If we reduce that noise, we're going to get a much cleaner signal, because what we're seeing across this set of scores is that even though people are kind of all over the place, wide variability in terms of scores for treatment A, B, and C, everybody's moving in the same direction, right? The change that we're seeing across individuals is fairly uniform and all the same. We can't see that in our between subjects design, but within subjects, we start to see this much more clearly. Okay? So if we go through and we think about from our one-way repeated measures ANOVA, okay? Here we're looking at, in our one-way design, similar to one-way to between groups ANOVA, we're looking at observations in a group of individuals across 2 or more assessments. Typically it's going to be 3 or more, because if it's 2, then we just use a paired sample t-test. But same thing with ANOVA. We can run an ANOVA, a one-way ANOVA in 2 different groups, right? We can actually just take that F test and take the square root of it and get a T, right? We can move back and forth. Same type of thing with our repeated measures ANOVA, right? But what we're going to do here is we're going to start parceling out this variability a little bit different, okay? So what we're going to start out is our sum of squares total, right? And so this is that treatment table that I in the previous slide, okay? So we've got 4 people, right? So we've got 4 participants. We're measuring them across 3 different time points, okay? And then what we have here is the mean across people's each individual score. So this is For individual one, this is their mean across treatment A, B, and C, mean across A, B, and C, mean across A, B, and C, right? This is our between, right? This is average score of treatment A, average score of treatment B, average score of treatment C, and this is our grand mean right here. And so what we're going to do with our repeated measure design is we're going to take, instead of, remember for our between, we're measuring things into within and within and between, right? Here what we're going to do is we're going to section out our between subjects, or well, let's start with our total. So our total score is going to be each person's individual score minus the grand mean, right? So if we take 2 minus this, 4 minus this, 7 minus this, 10 minus this, 12 minus this, square up those, and sum up those square deviations, this is going to give us the total variability in this set of data, right? So this is the total piece of pie we're working with. But then what we're going to do is we're going to section off our between subjects, right? Our between subjects are going to be pulled out as our individual subject means minus the grand mean and square those up, right? K is the number of treatments, right? So we've got the mean of our subject, right, minus the grand mean, and we're going to take that and square that. This subject's mean minus the grand mean, square that, this, that, and we're going to take that value, that sum value, and we're going to multiply it by the number of treatments we have, in this case 3, right? And what this is going to do is it's going to take our between subject stuff completely out. And if we go through and we take a look at this, right? So this is the differences across, these are our individual differences, right? So across treatments, we're getting quite a bit of variability here, right? These people, this person's real low, this person's real high, collapsing across stuff. We're going to take all that variability and we're going to suck it out, okay? We're going to take it over here. And so what we're going to be left with is our within subjects there, right? And with our within subjects there, what we're going to do is we're going to go down through and we're going to section off stuff that's just due to the effect of our repeated measure. This, right here is what we're really interested in, right? And so our repeated measure is going to be the mean of our repeated measure minus our grand mean. So on average, people's scores after treatment A minus the grand mean, treatment B minus the grand mean, treatment C minus the grand mean. We're going to take those square deviation scores, multiply it by the number of people in our sample, right? And that's going to give me my sum of squares repeated measure. And then my sum of squares error, because all of this, so we take the total, we subtract the between, we subtract the repeated measures, this is what we're left over with, right? And then if we wanted to go back to and get this is going to be our sum of squares total minus our sum of squares between, will give us our within here, okay? And so what we're doing, always thinking about our repeated measures design as first parceling out this between. The between is the individual differences stuff, right? Because in a one-way repeated measures design, what's our between or our between differences, which is the differences across individuals, right? So this is sucking out all this stuff. Angeline came to our study in a really crappy mood. Lauren was really happy. Sam lost his job, he's bummed out. Stephanie's in love with somebody, so she's over here. Katie's not paying attention to anything, right? Like all of this different stuff. This all gets captured in your between subject stuff and gets sucked right out, right? So as long as, no matter where you're coming in, if you're all responding to our manipulations in kind of the same way, that's sucking all that stuff out that would have otherwise went in your error term and would have swamped out your signal, okay? So always thinking about our repeated measures as first breaking our sum of squares total into between and our within. And again, the primary reason that we're calculating this is to sort of go through, gather up all the between subject stuff, the individual differences. Well, I'm not interested in you as a special flower, because you as a special flower screws up my study, right? What I want you to be is all the same, right? So all the differences that I can take across you, I can pull that out, remove that out of the error term to get a better signal, This is why our repeated measures designs end up being infinitely more powerful than our between subjects tests. Okay. Questions on this? All right. So for repeated measures ANOVA are some assumptions that we're working with here. Some of these are going to be familiar. We're assuming normality in the distribution of sample means. Again, this is a means-based approach, right? So really, from a technical standpoint, I'm not interested in the distribution of scores, right? Distribution of scores can be disgusting. As long as the distribution of sample means is reasonably expected to be normal, I'm going to be okay. So Sam, tell me under what conditions do I expect the distribution of sample means to be very quickly approach normality?
Your sample is 30 or above.
If I've got a reasonably sized cells, yep. What else? Right. So if whatever I'm measuring has a normal is expected to have a normal distribution in the population, then I'm going to be fine, right? Or if I have reasonably sized samples, then it's going to be fine, right? And so this starts to become important because some of the stuff that we're looking at, some of the constructs that we're interested in looking at aren't going to be normal in the population, right? So Lauren, if I'm thinking about alcohol use or substance use, right? Marijuana use probably doesn't have a normal distribution in the population, right? And so if I'm going through and pulling people in, I can't assume I'm going to get skewed data and my scores are going to have been looking at sort of days of consumption or something like that. It's going to be skewed, right? But as long as I can go through and anticipate that I'm going to have skewed data, and then just try and get reasonably sized cells for our means-based analyses, that addresses a lot of the stuff that we've got going on. Okay? So we can have, in our observed variables, in our observed data, we can have non-normality, and that's fine. We're not too worried about that, unless, one, we have small samples, right? If I'm working with cells of 15, it's just a hard thing to deal with, right? Because if I'm working with cells of 10, 15, something like that, one, I'm not robust to assumptions, or I may not be robust to my distributional assumptions. Also, if I have somebody who has a way high or way low score, if there's only 12 other or 10 other observations in that cell, that starts dragging that all over the place, right? If I've got 30, 35 people in my cell and someone's way the hell out here, it's probably not going to do too much, right? Because my sample size is big enough, so that's not going to influence it. But as soon as my samples get small, now all of a sudden I really start to have to worry about scores that might be real scores. They might actually be the people I'm most excited about, but they're just dragging everybody else out. So now it looks like people on average smoke a bowl a day, just because I've got one person in my sample of 5 people who do smoke, who's way out here. Now that makes everybody look like they're smoking a lot more than they are, right? So wanting to have cell sizes that are adequate to help make our analyses robust, but also remember if we start doubling down on violations, right? So if I have distributions that are a different shape and of unequal variance, if I have unequal variances, unequal sample sizes, huge violations of normality, small sample sizes, these are all situations under which if I'm screening these analyses, I start to become very concerned about potential consequences of things. Okay. So, but always remember that our assumption here is technically not with our observed data, it's the distribution of sample means. We're also worried about homogeneity of variance across treatments, okay? We want the variability at time 1 and time 2 and time 3. We're assuming that our variability across scores are going to be relatively equal, okay? We're going to look at this in our screen with our F max. Anybody remember what F max corresponds to? We could have done this in our between subject stuff. We didn't just because it gave us a Levine's test. We could also use F max. What is F max? This is our ratio of our smallest to our largest variance estimate, right? So we're going to go through and we're going to take, in our one-way repeated measures ANOVA design, I'm going to have time 1, time 2, time 3, and time 4, right? What I want to do is I'm going to go through and I'm going to find my smallest variance and my largest variance. I'm going to take the largest variance divided by the smallest variance. That's going to give me my X max, right? And in general, sort of my design is going to be fairly robust. 2 violations of homogeneity of variance. Remember that in unbalanced designs, we can start to have problems with inflation of type 1 error. If I have unbalanced designs, can I have an unbalanced design or repeated measures ANOVA? Should I have unbalanced designs? But this will become a problem as we start layering in between subject factor, right? Now, should I have group 1 and group, or condition A and condition B that I measure across 3 different time points? Then we can start having unbalanced cells. So important to remember that. In the one-way design, less of an issue, but wanting to know what Fmax is. Also remembering that Fmax is a ratio of variances, not of standard deviations. Okay, the ratio of 2 variances is not going to be equal to the ratio of the standard deviations. Make sure that you're calculating this correctly using the variance estimates and not the standard deviation estimates. All right, so that's stuff that we all know about and we're fine with. Okay. New stuff is assumptions about your variance covariance matrix. Okay, our repeated measures ANOVA. If we want to get into the deep nuts and bolts of this, we need to take a linear algebra course and get very comfortable working with matrices. Right? Again, you guys don't know how excited you are. Like, I've never made you invert matrices or derive coefficients from a regression model out of matrices and things like that. You think I'm a jerk and make you do a lot of things. I've cut things out that I'm not making you do. But I want you to understand from a repeated measures ANOVA, what we're doing is we're looking at a variance covariance matrix, kind of like what we have down here, right? And so in this case, we have treatment A, B, and C, A, B, and C. And what we've got here in the diagonal, this is the variance of each one of our repeated measures. In the off diagonal, this is the covariance, all right? So the variance of the measure, that's just for each repeated measure, the variance of scores within that, for that measure, right? Katie, what's covariance? You remember? Anybody remember what covariance is? What does it sound like? Look at that. It's two things sound vary in the same direction. Right? Your covariance is to a correlation as your standard deviation is to a variance estimate, right? Covariance is just a measure of the extent to which 2 variables change with one another, right? A standardized covariance estimate is just a correlation, okay? So essentially what your off diagonal is just sort of a raw, not really meaningful, just by giving it an eyeball look at the extent to which each one of your measurements is related to the next, okay? So think about covariance, so this being an unstandardized correlation in theory, right? So variability, right? So you can think about, if we were to go change this around to things that would kind of make more sense just to look at and interpret, this would be just standard deviations of scores for each time point. The off diagonal is going to be your correlations. Now, we're not using standard deviation correlations when we're actually calculating stuff, but conceptually, that's kind of what's going on with things. okay? So you can think about this as a correlation table, the correlation between time point 1, 2, and 3 with standard deviations on the diagonal, if you wanted to think about it that way. Okay? That's not what it is mathematically, but conceptually, it's kind of a similar thing. Okay? So, if we were to say this variance covariance matrix, okay? If we were to say that this variance covariance matrix met criteria for compound symmetry, we would say that the variances of our repeated measures, right? So the variability of each one of our repeated measures is equal across the population, and that all of these covariances are also equal. Okay? So compound symmetry says that the variability of each one of our repeated measures is identical in the population, and that the correlation between individual treatments is also identical. Okay? If your variance covariance met this requirement, we would say that it met criteria for compound symmetry. Now, compound symmetry, this is overly restrictive and not necessary for valid calculation or inferences from our repeated measures ANOVA. What our repeated measures ANOVA is assuming is something we call sphericity. Okay? Sphericity is, we're going to see sphericity when the difference score of each of our paired repeated measures is going to have equal population variance. Okay? And so what this is going to say is that in this sort of example here, so we've got T1 minus T2, we got T1 minus T3, T2 minus T3, right? Equals D1 is D2 is D3, right? Compound symmetry would say if we took the variance in each one of these different scores, right, for everybody. So this is saying for all 20 people in this study. If we subtracted, took the difference of time 1 and time 2, and calculated a variable for that, a difference between time 1 and time 3, time 2 and time 3, and we took a look at those different scores, compound or sphericity says that the difference scores of each one of these pairs is going to have the same variance in the population. So this is different. It's not necessarily saying that they're correlated all the same. It's just saying that the variance of the different scores of any combination of two time points is going to be the same, right? And so this is the formal assumption. And if we have violations of sphericity, what ends up happening is that our distribution, that our F ratios that we're going to calculate don't follow the standard distribution of the F ratios that we know and love, right? So this starts to become important. Just like thinking about Sobel. Remember the problem with Sobel is that the distribution of our test statistic doesn't actually map onto the distribution that we're using to drive the standard error, right? Same thing with our repeated measures designs. If we violate this sphericity assumption, the F tests that we calculate don't follow the F test that we're using to test, and so then things start to fall apart. This is a key feature of any type of violation of assumption, is when our distribution of our test statistics work fine as long as we're not violating assumptions, but as soon as we do, what we're getting is some coefficient, some statistic that doesn't follow the statistic that we're assuming it does when we're calculating our significance test, so things start to get thrown off there. So, if we have variance covariance matrices that meet compound symmetry, also going to meet sphericity. Okay, so if we've got this, this is going to be fine. But what we can get is that if I've got a variance covariance matrix that meets criteria for sphericity, it's not going to meet for compound symmetry, or it doesn't necessarily. It might not necessarily meet for compound symmetry. Okay. Now, this is getting into the math and like giving you an understanding. But if you do work with repeated measures designs and things along those lines, there's certain things that you'll be asked to do, expected to do, because of this violation of sphericity. And you want to know kind of what this means and why you're doing this and kind of where this stuff is coming through. Sometimes people have just been told, you always do this for that, and that's not always the case, right? So wanting to know kind of what some of these assumptions are, where these assumptions are coming from. So if we're thinking about this sphericity assumption, right? For between groups ANOVA, our between groups ANOVA also has an assumption of sphericity, right? So our between groups designs, we're assuming sphericity in our variance covariance matrix. The thing is that because we're not expecting there to be any relation between our individual scores and our individual groups, the assumption is just that the covariances are 0 and we don't worry about it, right? We just worry about variances in the diagonal, worry about homogeneity variance, and leave it at that. If our samples are, if our observations are independent of one another, we shouldn't see anything on the outs because we never talk about it, right? But it is an assumption of our between groups designs. It's just we're assuming that all those are 0, and that's almost guaranteed as long as we're collecting our data appropriately, right? With repeated measures in ANOVA, we expect the covariances between our assessment points aren't 0. So what we need to do is just make sure that they're all sort of being, so that the differences in the variability of the different scores across any two assessments is going to be identical. But the problem is that for our repeated measures designs, this is rarely the case, okay? And the problem is what I'm doing is I'm taking all of you, right? And I'm measuring your level of concentration and attentional control and alertness at the beginning of class and at 20 minutes and every 20 minutes as we go through, right? Now what's going to happen is if I measure your alertness at the beginning of class and 20 minutes from class, those are probably going to be pretty correlated with one another. But if I calculate your, and I find that I look at the correlation between your attention at the beginning of class and 20 minutes before the end of the class, some of you are going to be with me, some of you aren't, right? We're going to get a lot, it's going to be a much weaker correlation. So what we would assume with our repeated measures designs is that any of these repeated measures that are adjacent to one another are probably going to be more strongly correlated than stuff that's farther apart, right? So again, if I'm, Lauren, doing a study, I'm looking at substance use over the course of a semester, right? And I've got, 10 different assessment points, right? Drinking levels in between any two assessment points are probably going to be a lot stronger correlated than anything that I'm doing that's farther apart. And this is where we start to get into violations of sphericity, right? And so what we would expect if I were to, and sort of taking it back to sphericity, if I were to take the difference in drinking scores assessed 2 weeks apart, the variability of those of the different scores in those measures that are close is probably not going to be a whole lot, right? People are probably going to be pretty similar. I'm probably not going to have a whole lot of variability there. But if I take drinking at the beginning of the semester and at the end of the semester and take the differences in drinking there and then look at the variability across those different scores, it's probably going to be a lot larger than the variability of any two adjacent points, right? And so this is where we get violations of sphericity. This is a problem, and so what we do is we always assume that we're going to have a violation of sphericity, right? So the assumption mathematically to sort of visualize this, it might take you a moment to go through, but once you sort of understand it, from a practical standpoint, it's actually kind of easy because we just assume that it's always a violated, and then we're just going to proceed with corrected statistics. Okay. For 1,000 bonus points, under what conditions would we not have to worry about sphericity in a repeated measures design? Can we violate sphericity if we only have 2 time points? There's only one covariance there, right? There's only one variance to worry about, right? So this is the thing, people get all bent out of shape about sphericity and sort of crab at you about X, Y, and Z, right? But if you're running an analysis now, if we're doing it one way, then we're just probably using a paired sample test. But if we have a mixed design where we have, say, a 2x2 mixed ANOVA with repeated measures on the last factor, right? So I've got 2 groups that I followed across 2 time points, right? So I can't analyze that with a t-test. I need to use a mixed factors ANOVA. But sphericity in that case isn't an issue because I've only got one repeated assessment, and so it can't be different across things, right? So again, this is where understanding the assumption can help in terms of when you present stuff, and people are like, oh, you have to do X, Y, and Z, but well, actually, no, because that's not a concern in this situation. So what we do with our repeated measures designs, and there's different ways to do this. There's ANOVA approaches that I wouldn't recommend because we have corrections to our F test that sort of do a reasonable job of correcting for violations of sphericity. Our Moxley test will tell us whether or not we have, that is provided in SPSS, this will tell us whether or not we have violations of sphericity. Problem is that this test underpowered, sensitive violations of normality. So even though SPSS will give you this, ignore it. And we'll just assume that we violated assumptions of normality, just move forward, okay? And so what we see with our correction, for our corrected statistics generally involve primarily downward adjustment of your degrees of freedom, okay? So what we're going to do with these corrected test statistics for your omnibus effects, most of what's going on there is you're going to make an adjustment in degrees of freedom. So if I have a, say, 50 degrees of freedom, right, and I get a correction for that statistic, and I now am estimating this at degrees of freedom equal to 34.6. What did that downward adjustment to my degrees of freedom just do to my test of significance? What do you think, Angela? What's that? Yeah, so the degrees of freedom on my test, I actually, my design has 50 degrees of freedom, but I've made a correction, so now I'm testing it against 32 degrees of freedom or something. What's that?
So you're testing it against a more stringent.
Exactly, it's more stringent, right? And so if I were to issue is in my repeated measures design, if I just look at my uncorrected test statistic, I might find that, oh, yay, I'm excited about this, it looks good. What these corrections will do is set this as at a more stringent test, okay? And so this downward adjustment of our degrees of freedom depends on the extent of the violation as calculated by the correction. Violation is indexed by epsilon here. Nope, sigma, that's small sigma. That's small sigma, not big sigma, tiny sigma. Right? Tiny sigma equals 1. This indicates that sphericity assumption has been met. If epsilon is equal, or sigma is equal to 1, epsilon, sigma equal to 1, we've got no violation of assumption of a sphericity, but as that value decreases, we get more and more of a correction for our violation there. A couple of different corrections that we have available to us in SPSS. Greenhouse geyser correction, we're adjusting your degrees of freedom based on greenhouse geysers correction or variation on sigma, okay? This is often indicated as sigma hat, okay? You've got a Hohenfeld correction that's using a slightly different version of this. What ends up happening is Hohenfeld assigns less of a penalty than greenhouse geyser, right? We typically use greenhouse geyser as the more conservative of the tests. There are situations where you might use Hohenfeld is if you have in the uncorrected tests, you have a significant omnibus effect. Greenhouse geyser, it's not reaching significance. Hohenfeld's probably going to be somewhere in the middle. You can make an argument then we're going to go look at Hohenfeld if the true value of epsilon, or excuse me, sigma, estimated at not below 0.75, but for the most part, and again with these types of designs, you generally will just have a good deal of power. Just go ahead and work with your greenhouse geyser. If you ever wanted to dip your toe into Hohenfeld, note that the correction provided by SPSS and SAS isn't right. So be aware of that. Make sure you go through and calculate that on your own if you were to want to go through and use that correction there. Okay. All right. Let's stop there, take 10 minutes for a break, and come back in, and we'll jump into some actual testing some stuff. All right. So, tying this all together so that people would sort of have a good conceptualization of what we're doing with these repeated measure designs. If we're looking at people only one time, if we only get scores from individuals on one occasion, all of that individual differences that people come in, all of those differences get relegated to the error term, right? And so if we've got a really strong between groups effect, then that's fine. But if not, those individual differences can go through and swamp things out, okay? But when we take a look at individuals repeatedly, if we're looking at people again and again over time, what we can do is we can model those individual differences, pull those out of the error term, and what ends up happening is we get a much, much stronger test of whatever it is that we're looking at, okay? The greater the differences across people, right? The more variability we get, the higher the correlation across individuals, higher treatment, the correlation between our treatments, greater power of repeated measure designs, okay? And so, Angela, in your guys' lab, what bio or physiological measures do you all take?
Right now we're doing EKGs.
EKGs?
Yeah.
Okay, so just heart rhythm waveforms?
Heart rate variability.
Heart rate
and,
variability.
like muscle. And so what are those, EMGs?
EMG stuff.
EMGs.
Yeah. Okay, so I've used heart rate variability stuff before, and like that's going to be really like. So my dissertation, I went through and sort of was measuring heart rate and skin conductance and heart rate variability types of stuff, right? And showing people some really terrible films, right? Like here's a test pattern. Now here's a really terrible, awful film, right? And expecting, obviously, that.
Poor quality? Like what terrible?
It was supposed to. It was a trauma analog study, and so this was something intended to simulate shock and those in a controlled setting, right? And so again, we saw changes in skin conductance, changes in heart rate, heart rate variability, nothing. Didn't change at all, right? And so something like that is going to be very stable, right? So if I have people sitting down and test in a experiment that contains physiological variables, and I'm sitting people down and I have them sit in like a half an hour participation session where we're measuring stuff at different time points, all of those measures are going to be correlated 0.85 and above probably with one another. Huge correlations between repeated measures. That's going to be an incredibly powerful test. Very subtle differences across in mean values across those time points are going to be able to be caught just given the high correlation across your time points there. Okay, so again, this is the whole reason behind going through and doing this. I said it last semester. I'll say it again. If you can go through and incorporate repeated measures designs into your studies, you're going to be in good shape. So, a couple of examples we're going to go through. A little bit different. This starts to have an impact on how we go through and run some follow-up tests on whether or not your means across time have some specific order to them that's logical and meaningful, or if they don't. If it's just, I could flip time 1, 2, 3, 4 all around, it doesn't actually matter at all, okay? So for this first set we're going to look at, what we're interested in is whether or not depression scores, self-reported depression scores, are going to change over the course of 6-week inpatient treatment. So here we go. This is serious mental illness stuff. We've got an inpatient We've got to give them some treatment. What we want to see is hopefully that we see change in depression scores over the course of intervention, right? And so here are depression symptoms at intake, 2 weeks, 4 weeks, 6 weeks, and hoping to see some sort of change going on there, right? And so in this case, the order of our means something, right? If I shuffle these around and put 4-week symptoms first, and then 6-week symptoms, and then intake, and then 2 weeks, that screws up the whole thing. That doesn't make any sense, right? And so in this example, the order of the means in which we're collecting those mean something, okay? Here in the second example, this is a study I put together, and this is something that I intentionally developed as a within subjects design because I was terrified that I couldn't do this in between subjects or I just wouldn't find anything, right? And so what I did is, so we brought people in and asked them, gave them a vignette of a hypothetical victim of someone who had experienced significant life stress, okay? I say, here's AF. AF experienced this, AF is reacting this way. How willing would you be to provide AF with basic or maintain friendship with AF, right? And what we did is we had people sit down and they read multiple vignettes in this study. One was motor vehicle, someone who'd been involved in a motor vehicle accident, someone who had been deployed to combat, someone who had experienced relationship infidelity, sexual assault, natural disaster, chronic illness, having to move for work, financial ruin, right? So we've got some things in this these scenarios that are trauma related, and some stuff that's super, super stressful, bad news, but not something that we would call a trauma, right? But with this, right, I'm going to ask people, here's a vignette. How willing are you to remain friends with that person? What are people going to say? Yeah, right? I mean, I'm asking them a loaded question. Someone just went through a horrible natural disaster. How willing are you to maintain friendship with them? Screw that guy. No, right? This is not going to happen, right? So I'm not going to probably get shocked. It's a loaded question. People are probably going to say yes more often or rate higher than no. Also, I've got a lot of different things that I want to take a look at. Right now, if I wanted to look at this and adequately power differences across these responses to these different vignettes with a between subjects design, I don't even know what that sample size would have to look like, because if I just had people sit down and you're in this condition, if I turn this into 8 different conditions, and to get enough people in each one of those cells to reasonably tease apart differences here, that's never going to work. It's never going to happen. But if I go through and I turn this into a repeated measure design, right? And I sit Sam down, I say, hey Sam, here's 8 different vignettes. Go through, read it, and then respond. Tell me how much you're willing to provide friendship, provide support, blah, blah. We have to do a bunch of stuff, right? Then I've got Sam giving me responses across all 8 of these, right? And so we ended up in this study counterbalancing this, right? So the order of the vignettes change across individuals. But then in this study, Sam ends up being his own control. So if Sam's a jerk, he's not willing to be friends with anybody, Sam's got low scores across all of these, right? As opposed to having to account for individual differences across people, okay? So let's start with the ordered means example. So if you open up belief ratings, ordered means, okay? You can see here, and if you pull out your example, what we've got is depression scores at time at intake, 2 weeks, 4 weeks, 6 weeks, okay? And so what we want to do maybe first here is go through and we'll analyze. We'll do this real quick. We've got our descriptives. So if we look at our distributions, it's not looking too bad, right? Skew look a little positive skew, positive kurtosis. So we're not terribly concerned with that. If I go through and explore. That's not too bad, right? That's looking okay. That's also looking pretty nice. A little bit of a positive skew there, but again, we've got 388 people in this sample, so I'm not too concerned about the distributions here, right? We've got more of a severe score at 4 weeks, right? More of a score at 6 weeks. So clinical people, what's going on here? So we start out with a distribution that looks pretty nice and normal. A little bit of skew, more skew, prominent skew. What happens? What's happening here?
We're getting less sad over time.
We-
We're reporting less symptoms of depression over time.
Okay, so it looks like the mean shifting, but why is my distribution shifting? So basically, majority of people are responding, and they're starting to get smaller, but we've got people who are not getting better, and they're staying where they're at, and so we're starting to see increasing skew across repeated assessments. This is not atypical stuff that you'll see, right? And in here, we don't have a whole lot of attrition because they're inpatient, they can't go anywhere, right? So they're kind of captured audience and following people along here. But overall, by the time we get to this point, we've got some skewed and probably some things that are going to be outliers. Am I going to be too worried about doing something with those outliers, throwing them out? Why not? They're not unexpected, and certainly I don't want to be throwing people out that just aren't responding to my treatment. What other aspect of this makes me less concerned about these potential outlying values? Okay, so we're going to see some patterns. What's kind of the fundamental thing going on here? So I got somebody's case number 84, or person 84 in the sequence has a pretty high depression score relative to everybody else at the rest. Why am I not concerned about that score screwing up my mean? Yeah, I got close to 400 people. So that person, I'm really not worried about the impact of their score on my thing, right? So these are the things that are important as we're going through. If I were to screen these data appropriately and go through and identify Z-scores and things like that, by the time I get to the end, I'm probably going to find some scores that are several standard deviations above the mean, right? But given that we're working with means-based analyses, right? So I'm not worried necessarily about the distribution of my observed scores, worried about the distribution of sample means. Distribution of sample means is going to be fine with a score with a sample of close to 400. Yeah, it's going to be fine, right? And am I too worried about outliers? No. That person's probably not going to go. Now, if we're looking like something at income, right, and someone's making like $17 million at the end of the study, then that's something. But again, this is a self-report measure. You can only answer so high, right? And so the impact of this is going to be minimal. And the risk I run by starting throwing people out or recommending people be kicked out of the study is I'm systematically excluding people that aren't responding to my treatment. And that makes my treatment look a lot better than it probably is, right? So I'm wanting to think about the consequences of this stuff. So let's go through, take a look at my correlations here, just to see strength of associations between my scores. And so I can see very clearly here, right, that correlations between adjacent time points intake in 2 weeks, right, and 4 weeks and 6 weeks, and 4 weeks and 2 weeks, these are all pretty strong, right? But as soon as I get on the off ones, if I look at the correlation of intake and final, I mean, it's still a decent correlation, but it's much less, right? And so you can start to see, like, this isn't, again, sphericity is based on variability of the difference of scores in pairs, but you can start to see how this is probably a very clear violation of compound symmetry, right? In that scores that are closer in time point are more strongly correlated than scores that are farther apart. And so this is the type of thing that we need to keep an eye on for in terms of violations of homogeneity variance and things like that, right? And so, Katie, to your point, here, if someone, maybe say I was missing, having been missing in this set, someone just didn't get assessed at week 4, right? So I've got, in this study, I've got 15 people who you're missing scores for at time 4, or at week 4. Probably an expectation maximization or some other type of more sophisticated imputation approach is going to do a pretty nice job of recovering or estimated likely scores. One, because if I got 15 people missing in a sample of 400, that's a small proportion of my total scores. We've got strong correlations between my measures, right? And so the ability of these data to provide some reasonable estimation of stuff to go in there is probably going to be pretty big, right? You have to go through, figure out what type of program you're going to use, how you're going to do that, but something that you could use in sort of scenario that you did before. So what we're going to do, though, is our question is, do we see differences in this repeated measure over time? So what we're going to do is we're going to go to Analyze, and we're going to go to General Linear Model and down to Repeated Measures. Okay. We're going to name our factor, right? I'm going to name this factor, what do I name this factor? Time. We'll name it assess because apparently that's what I named it on the handout there. And I've got 4 repeated measures, so there's 4 levels to my repeated time point. So I'm going to hit add. I'm going to hit define. Now with this simple design, all I do is I say, all right, I got intake, 2 weeks, 4 weeks, 6 weeks, I'm good to go. Okay. And then I'm going to go contrasts. It's going to be polynomial. We'll leave that alone. Plots. We'll put our assessment points on horizontal and horizontal axis. Hit continue there. And then on my options, we'll ask for display means for assessments, and then I'll ask for descriptive statistics, effect sizes, homogeneity, and we'll do that as it is. Okay. So we'll hit OK there. All right. People follow me up to this point? Okay. You can hit paste. I'm going to hit OK. Okay. So what we get at the very first top of this, right, we get a warning that says homogeneity specification in the print subcommand will be ignored because there are no between subject factors. Homogeneity, we can request this, but it's going to give us our Levine's test for between violations of a homogeneity of variance if we have a between subject factor at each factor. So if this was a 2x4 design, which we'll get into at some point, right? So we've got this group versus that group, right? Across 4 assessment points. So we've got a between subjects factor within subjects factor. And what this is going to do is if I were to request homogeneity of variance test, it's going to test homogeneity of variance at each one of those time points, right? But here we don't have a between subjects factor, so SPSS told me, no, I'm not going to do that. I'm just going to ignore it, which is fine. They can do that. I'm going to go through, take a look at my within subjects factors, making sure that this, always check this to make sure that you've got this loaded up in the order that you want them to be ordered up. PDI 1, 2, 3, and 4. Here we've got our descriptive statistics, okay? If we're looking at our descriptives, what do we like about the descriptive statistics? Just kind of looking at this. It's going down, cool, right? It looks like that certainly with a sample of about 400 people, I should probably see some sort of change here in what I've got going on, right? So this is good, just as a screen. What am I, in terms of my assumptions, what am I going to be looking at, or could I derive here to take a look at? What could I calculate? What do you think, Angela? Not my T. Homogeneity variance, right? I'm going to take a look at my F max, right? So here, if I pull this up, what I want to do is I want to find my lowest variance and my largest variance. Where do I have the lowest variance at? 6, and my highest? Intake, right? And so remember that this is a ratio of variances, not standard deviation. So I'm going to take 12.688, and I'm going to square that, and I'm going to 9.551. I'm going to square that. I'm going to divide those two. I get an F max statistic of 1.76. That's well within reason. I'm fine with that, right? There's no concerns going on there, right? And so in my screening, you don't have to do that. I mean, you can also just request variances in your screener when you're asking for your descriptives and just calculate it from there. Only thing to remember is just remember that you're doing this with variances and not standard deviations, right? So my F max, and so just to show that, so go through and take 12.688 and divide that by 9.551. What do you get there? 1.33, right? It's smaller, right? Because again, it's not like we're multiplying these by a factor of 2, which would make that ratio the same. We're squaring these. So larger numbers get much more large when you square them than smaller numbers, right? So what ends up happening is you would be underestimating that F max ratio if you're dividing standard deviation. So make sure you're using variances there, okay? So you've got multivariate tests. One way that people will talk about looking at repeated measures is using a ANOVA approach, right? So the question here would be if we had a between subjects type of approaches, like is there a difference in the best linear combinations of our repeated assessments, right? But this is actually not a great way to go through and look at it for a number of reasons. It's not going to be consistent with how people are typically reporting it. If you've got really high correlation between your repeated measures, your ANOVA is not going to have actually a great deal of, it's going to have some problems with some power anyway if everything's super highly correlated. Highly correlated repeated measures are actually a strength of the repeated measures design. So multivariate tests, scratch those. Don't worry about those. Don't get confused and start reporting things out of this table. Don't worry about that one. But then we get down into Mauchly's test of sphericity. Do we pay attention to this? No, we don't. Because we know that this is like many of our other tests, right? It's sensitive to violations of normality in our data. Our data aren't terribly non-normal, but by the time we get to the end, we've got clear skew there, right? We've also got an obscene number of people in this sample, right? It's going to make it super sensitive. And so what we can see is that this would say, yes, that we've violated our sphericity given our significant value here. Are we shocked by that? No. We kind of expected that anyway. We walked in knowing that this was going to be the game we're playing. And so we just ignore this, right? You see here at the end, epsilon values for greenhouse geyser, Hunfeld. Hunfeld's wrong, so don't ignore that. If you want to use Hunfeld, make sure you're calculating it by hand. But this is, again, these epsilon values are a measure of the extent to which you violated sphericity. One being no violation, and then as that value starts to get smaller, increasing violations, right? So again, know what those are. You don't have to do anything necessarily with them. Just kind of be aware of what's going on here, okay? So what we're gonna go down through is your test of within subjects effects. This is kind of where your business is. It's where you're going to be most interested in stuff. So remember that we've got sum of squares total sum of squares between sum of squares within sum of squares repeated measure sum of squares error. Okay. Remember that this is the breakdown for our one-way repeated measures ANOVA design, right? So what you want to do is know where to find these different figures on this thing here, okay? We see on our test of within subjects effects. Laser the thing that's actually on the camera, so if you guys are watching this later. All right. We have our measure an effective assess. Okay, Morgan, what is this telling us? This effective assess.
That the difference is not zero?
What? Well, and not make sure that we're not talking about. We've got multiple things, so we can't say the difference, but some difference. It looks to be different than zero. So what? How are we interpreting this effective assessment?
There's an effect somewhere?
Right. So it's saying, the omnibus test is saying that we're seeing some change across these repeated assessments somewhere, right? Now, this is a one-way repeated measures design, so there's only one place for us to see differences, right? We don't know what those differences are, but it's saying that there's some difference across our repeated measure somewhere, right? Our null hypothesis is that mean at time 1 will be equal to mean at time 2 equal to mean at time 3 to equal to mean at time 4, so on, right? And then our alternative is that at least one of those are going to be different than another one, right? We don't give that notation because there's a lot of different ways that those could be different, right? And so here, you'll notice that our F-test is actually identical across all of these corrections. This is going to be the case with our one-way design, okay? But typically what we would do is go through, take a look at our greenhouse geyser correction, because sphericity assumed, do we ever assume sphericity? Nope, right? So we go down through, take a look at our greenhouse geyser. We see that we clearly have an effect here. If we look at our partial eta squared, what is it, Sam, what does that suggest about our effect? What's that?
Is it large?
It's massive, okay? Remember, this partial eta squared is a proportion of variance estimate, right? We'll talk about kind of what those things are doing in just a moment. But essentially what this is saying, we have a very clear and strong effect. There are changes in average levels of depression somewhere in all of this, okay? So this sums of squares estimate for our greenhouse geyser, where is that going in my sort of tree right here? What do you think, Katie? Yeah, where's that going in that tree? What does this sum of squares correspond to? I'm seeing hand movements from Alex. What are you thinking, Alex?
Is it within the sum of squares?
Getting closer. You're getting hotter.
And then maybe going down to the R end?
So what does this correspond to? What do you think, Sam? Yeah, it's my repeated measure, right? This is my in this design, like, this is my effect. The sum of squares of my repeated measure, that's the effect that I'm interested in. And so my sum of squares here for assess, this is my sum of squares repeated measure, right? Sam, what about my sum of squares error? Where am I finding this?
On the bottom.
Hold on.
Yeah, so sum of squares for my error is going to be this guy right here. Okay, what's that?
Okay, so is it sum of squares between or sum of squares repeated measure? Because you said both for a hot set there.
Oh, no. So this is my sum of squares effect. So it's my repeated measure, right? This is what I'm interested in, right? So my sum of squares repeated measure. So are there differences in my repeated measure across assessment points? This is the effect I'm looking at. So this goes right here, right? But if we look at this is our test of within subjects effects, right? So this table corresponds to this piece right here, right? And so here we've got our sum of squares for our repeated measure, and here are sum of squares for our error term, for our within subjects error term, okay? Now if we go down, and then below this we see, well, skip sum of squares within contrast for a moment. Drop down to this test of between subjects effects, right? Katie, what is this giving us here, our error term here? What's that give us?
Sum of squares between.
That's our sum of squares between. This is where all our individual differences get sucked out, okay? This is where everything gets pulled off to the side. And so this error component, excuse me, I'm sort of waving things around down here, so our error in our test of between subjects effects, this is that sum of squares between, right? And this is a huge chunk, right? This gets all sucked out, right? If we can make our error term really, really massive, right? But what we've done is we've sectioned out, put that over on this branch of the tree, and what we're primarily interested here is our test of within subjects effects, right? And here we have very strong support for the fact that these repeated measures are changing over assessment point in some way. So Katie, if I wanted to get my sum of squares within, how would I calculate that?
Add the sum of squares between and the sum of squares are in the S's there.
Yep, I would go through, I would add this, that gives me this, right? What if I want to get my sum of squares total, how would I do that?
Add the sum of squares within with the sum of squares between.
Yep, well, I could do that, or I could take the sum of squares for my repeated measures, sum of squares within, plus sum of squares between, add those all together, right? And this is going to start to become important when we start to try and calculate appropriate effect size. We have problems with our partial A squared. And we'll talk about what our concerns with effect sizes in their calculation is sort of the theme of this sequence in a lot of ways, but wanting to know where these different pieces and parts are coming from, so you can go through and identify that, okay? So, here's our estimated our marginal means. I mean, in general, when you're writing things up, provide actual observed means. Those are more informative. But you've got your marginal means here. And someone tell me, Stephanie, tell me what's going on in terms of our means. What are those doing across time? Decreasing very clearly, right? And so we're going to get, so right now we're just working with our omnibus effect here. But for our one-way omnibus test, we're just looking up here at our main effective assessment, and we're saying that this significance omnibus test is saying that the pattern of means across assessment points is changing, or that means are different across assessment points, things along those lines. Okay. And I mean, like any other ANOVA, we'll need to go through and start teasing things apart to see where these are going on, but we can eyeball this and have a pretty good sense of what's happening with this, right? Cool. All right, so this is what it might look like if we were running ordered means. But sometimes means aren't ordered, right? In our survey study, where we're asking people whether or not they're going to be nice to people who've experienced stress and trauma, it doesn't matter, right? We actually, in actual fact, collected these means we counterbalanced this, right? So different people got different orders, which is important, right? So you don't want to say, having to move for work seems less consequential if I just read a scenario about sexual assault, right? So we're just changing these up to try and account for the fact that people may have carryover reactions to different things. So counterbalance design And what we're going to do is we just want to see if we see, on average, differences in ratings of people's willingness to provide friendship across these different vignettes. So this is going to be your other handout that you got. If you go through and you take a look at this, you'll see if we take a look at our correlations here, these look a little more uniform, maybe than the last one, right? Because again, these are all counterbalanced in terms of the ordering and things along those lines. But we still have a problem with, potential problem with severity, because it's likely that given some of the thematic differences in or thematic similarities in some of these types of, some of these vignettes, some of these are probably just objectively will be perceived as more severe than others, right? And so it's probably across 8 different vignettes, it's probably not reasonable to assume that all the variability of all possible different scores in these are all going to be identical. So we've still got some problems with this, right? But if we go through and we run our analyses, what we're going to do is we're going to go analyze, general linear model, repeated measures, and here we'll name this, what do we name this? Grading. You can name it whatever you want. But we've got 8 levels to this, right? So we give you 8 different vignettes. I'm going to hit define. And what I'm going to do is I am going to be strategic. And what I'm going to do is I'm going to put in MBA, combat, and I'm going to put in assault and disaster. So I'm going to order my trauma-focused vignettes first, and then follow up with infidelity, illness, relocation, and financial ruin. Okay. I am going to go here. Our contrasts don't make a lot of difference here, and so we'll talk about why that is. But we'll still rate our plots, look at our individual ratings on a horizontal axis and plot those out. And then I'm going to drop down, I'll say options, display means for this, I'll say descriptive statistics. I won't ask for homogeneity tests because it won't give it to me anyway because we don't have a between subjects factor. Estimates of effect size. Sounds good. Okay. You with me? All right, we'll go ahead and hit OK here. Same thing as before. Always wanted to go through, take a look at my within subjects factors, make sure that I know what order these are in. This is going to start to become important as I start thinking about how I'm going to tease things apart and test and stuff. So we've got friendship, war, or excuse me, car accident, combat, sexual assault, disaster. Everything's looking good there in terms of how I've ordered it. F-max ratio, again, could go through, want to calculate my F-max. Here, if I calculate my F-max, I'm going to get a value of about 3.1. Again, if I find the smallest variance and the largest variance, calculate the ratio between those two. That's going to give me my F-max. So this is going to be actually bigger than what I had before. So my largest variance is for infidelity on people's willingness to keep friends after someone cheats. So take that variance and divide that by, it looks like, lowest variability in terms of accident involvement, 0.77, square that. Yeah, I get a, oh, whoops, no, that's not 3.1, that's bigger, that's 3.7. Is that right? Yeah. 1.351. Take the square of that, 0.77. So I've got an F-max of 3.1 here. Okay. So again, not something that I'm probably going to be worried about, but this starts to tell me something about my data. Okay? Morgan, what does this tell me about my data?
I'm not quite sure. I don't feel like maybe I have a very good understanding of the F-max calculation in the first place.
Okay. So F-max is just the looking at the assessment with the greatest amount of variability over the top of the assessment with the least amount of variability. And at least based on this F max that we've got, what does this tell us about, what might we start to infer about people's reactions to these different scenarios or vignettes? Right? And this can start to become important, right? It looks like people don't respond uniformly to these different scenarios, right? For car accident stuff, people, I don't know, I haven't looked at I mean, I'm looking at the means here, I guess, but it looks like people are working pretty closely around this mean value, right? And this is a 0 to 8 scale. People are topping this out, right? On average, a randomly selected person is about 3/4 of a point off of that mean value, right? So we've got pretty good consistency here, but people's response to perceived infidelity or instances of infidelity, you get more variability in terms of that stuff, right? And so this is just telling us as we're going through and screening our data, remember that this isn't just something to do because I'm a mean person and I'm forcing you to do it. It starts to tell us and give us insight into what's going on with these scores, right? I start to get context around this. It looks like literally close to 4 times the amount of variability in terms of how people are responding to this infidelity vignette as opposed to how people are responding to the car accident vignette, right? This kind of tells us something that's could probably, and it's probably important if we start thinking about how we're going to discuss what's going on with this. Okay. So, going down through, again, multivariate test, we're ignoring that. Our sphericity assumption, we're just assuming that we're violating sphericity anyway, so we're just going to ignore that, right? We come down and look at our test of within subjects effects. What does Stephanie? What are our within subjects effects telling us here?
That the difference in willingness to provide friendship or the difference in between the different scenarios is not.
Well, they're just different, right? Again, so I mean, you could say the variability is not equal to 0, I guess, if you wanted to. But just in layman's terms, right? We're just saying that based on this analysis, it looks like mean levels of mean friendship ratings are differ across different vignettes. Okay. So this is good, right? It looks like people are responding, systematically responding differently to different scenarios placed in front of them. Okay. We're going to see ignore within subjects contrasts. Here are between subjects effects. This is variability that's due to just individual differences. Some people are more friendly than other people. Some people are more susceptible to response biases, right? And boy, I don't want to say that I'm not going to be friends with anybody who just went through something tough. So I'm just going to put 8s across the board. Versus Sam, he's a mean cat from the streets. He's like, I'm going to help anybody, right? What are you going to do for me, right? It's like, maybe, maybe not. We'll see what happens, right? Did you deserve it, right? I'll cut you, right? He's a hard guy, right? So but we're cutting all that stuff out and putting that in our between subjects variability so that it's not interfering with stuff, right? And if we go down through and take a look at what our means are with this, Katie, at first glance, what does it look like here? That they vary, yeah. And then kind of this graph kind of makes it look like they differ by quite a bit, right? What do we get at second glance, Angeline? What's that?
The y-axis?
Yeah, what's on the y-axis?
It's dropping by 0.1.
Yeah, I mean, it was at 7.1 to 7.7. This is a 0 to 8 scale, right? If we were to plot this on a 0 to 8 scale, it's going to look almost like a flat line, right? The differences that we're seeing in here are very, very subtle. These are very, very minor, right? If I were to have gone through and collected 30 people to complete each one of these different scenarios, would I have found a difference in average scores? Absolutely not, not even close, right? But here what we've done is we've capitalized on the repeated measures design where people are serving as their own controls, right? So you might, in general, provide very high ratings of willingness to maintain friendship. Katie, we've established she's mean. She might provide more modest and perhaps realistic levels of willingness to provide friendship, right? But differences across Katie's scores and differences across other people's scores are all sort of made within the context of previous scores, right? And so what we're looking at is systematic differences after we pull out that individual differences stuff. And what we end up with is a much, much more sensitive test for differences that we probably wouldn't have detected otherwise, right? I don't know how many people I would have to get to complete each one of these vignettes to tease some of this stuff apart in a between subjects design, but it would be massive. I would still, I decided what I think is collected this data in 2014. I'd still be collecting and trying to get enough people to actually tease stuff apart in this, right? But if we set it up in a repeated measures design, right? And so taking into account the fact that we're going to have carryover effect, right? So we're going to counterbalance the order in which people are responding to these. We're starting to see, based on our repeated measures ANOVA, that we do see systematic differences in the means that people are providing across this over time. Okay. Questions about this? Questions about interpretation of your ANOVA output, what any of these figures are? Okay, cool. So let's jump back in. And finish up talking about some effect size stuff. So remember that if we're talking about our eta squared, eta squared is giving us a portion of total variance that's attributable to an effect in our data, right? And this eta squared is just going to be our sum of squares effect over our sum of squares total, right? So we're, in this case, we take sum of squares repeated measure divided by sum of squares total. Okay, that gives us our eta squared. But we know that our eta squared value is going to be sensitive to how many effects we have in our design, just like with our between subjects ANOVA, right? Here, in say, if we're going back to our between subjects design, a 2x2 is going to have a sum of squares effect for factor A, factor B, the interaction, right? All of this stuff is getting included in the denominator of our eta squared, even though these are factors that we've accounted for, right? It's not error, right? We're looking at the unique variability that we're accounting for, but it's not error, right? And so what ends up happening then, as particularly if we have correlated effects, right? What ends up happening is our eta squared starts to become smaller as we start to add more effects in, because of just random overlap with some stuff. And so if I have, I'm looking at an eta squared for a 2x2 ANOVA versus a 3x4 ANOVA, right? There's more stuff going in here, right? That's going to start to, or excuse me, not a 3x4, but a 2x2x2, something like that, right? So this is going to start to get smaller and smaller as part of my effect here starts to get sucked off into other things, right? And so what we're going to consume is that our eta squared might be an underestimation of the general size of our effect. So we have our partial eta squared, right? We talked about partial eta squared before. This is looking at the size of our effect relative to unexplained variance. So in this case, we've got our sum of squares effect over our sum of squares effect plus sum of squares error, right? And so what we're going to do is we're going to take everything that we've accounted for. We're going to section this off to the side, and we're just going to look at the sum of squares effect over our sum of squares effect plus error, stuff that we haven't accounted for, and that's going to be our partial eta squared. What does this sound like? partial correlation, right? It's the same idea, it's the same stuff, right? But the problem here, so what we do is we capitalize on other variables as controls, and we're just looking at of the stuff that we haven't explained, sort of what is this accounting for? Okay? And so if we were to calculate partial eta squared that you found in your SPSS output, right? This is going to be, we're going to take our sum of squares effect, which is our repeated measure, and we're going to take our repeated measure, the sum of squares for a repeated measure over the sum of squares with repeated measure plus the sum of squares error, and that's going to be our partial eta squared, right? Partial eta squared in our unordered means was 0.08, right? So that's not a huge amount, but it's bigger, right? Our partial eta squared for our depression scores was massive. It was like 0.5 something, right? That's nuts. But it's really big, right? But the problem is, within our repeated measures designs, we've got multiple sources of error, right? And what ends up happening is we're concerned that our partial eta squared is going to be too big if we're only looking at the error term of an individual effect. Because when I calculated my partial eta squared for all the individual differences here, right? And so what we've got is people have suggested calculation of a generalized eta squared, right? Generalized eta squared, what you're doing is you're accounting for all sources of unexplained variance when you're calculating your effect size, okay? We can easily get this from our SPSS. It's just we need to go through and determine one of the things that happens within our calculating our generalized eta squared. I can't give you a formula for generalized eta squared. Because generalized eta squared is going to depend on how you set up your study, the design of your study, and what effect you're interested in. Right? And so this starts to become complicated because depending on what your design looks like, your procedures for calculating generalized eta squared is going to be different. Now for our one-way repeated measure ANOVA, our generalized eta squared is going to be our sum squares for our repeated measure over our sum squares from our repeated measure plus our between plus our error here. Essentially, it's sum squares of repeated measure over sum squares total, which is essentially eta squared, right? But we saw the same thing happen when we were talking with one-way ANOVA before. Partial eta squared reduces to eta squared. Same type of situation here, right? But in most cases, we'll see that our eta squared is going to be smaller than our generalized eta squared, which is going to be smaller than our partial eta squared. In this case, in the one-way case, generalized eta is going to be equal to eta squared, right? But as we go through, and I've got a Bateman article that will go through and lay out how you go through and calculate generalized eta squared for repeated measures designs, okay? And so what ends up happening with our generalized eta squared is it's nice, it's flexible, because it's taking into account aspects of the design to go through and provide an appropriate measure of effect size that's going to be generally comparable across studies. So Anjan does a study with a design that's a little bit different than Katie's. If both of you are calculating generalized eta squared for your effective interest, it should be reasonably comparable as a metric to look across this, so that we don't end up getting huge differences in the effect size based on the specific nature of the design. Okay, and so in our last set, what I'll have you do, read this and go through and calculate generalized eta squared for some different parts of the design that are going to be different depending on the example that we're providing. Okay. Questions? All right. That's what I'm going to do. Calculating effect sizes for this last example is pretty easy. I've got a screencast that's brief that kind of walks through the calculation of all that. We'll save some time. I'll have you watch that. You could probably figure it out real quick just based on the discussion that we've had. But if you want to go through, I'll post that, make that, I don't have to make that link available. It's on YouTube for everybody to see. Right? It's probably got at least 50 million views by this point. It's been up for a whole semester. But I can go through and help you get squared away on that. So, next thing that we've got to take care of, though, is determining our specific effect. So our omnibus effect tells us that, yes, our means are different across assessment points, right? Somewhere in there, at least one of these means, one of these repeated measures is reliably different than the others, right? But the question then becomes, how do we go through and tease that apart? This can get really tricky with our repeated measures designs, particularly as we start to transition into mixed effects or mixed factorial designs, where we have betweens, withins, that type of thing, okay? But in general, just as a review, again, our repeated measure designs are kind of tricky. We've got different assumptions. We've got the possibility of both between and within designs that we need to take account of. If we're going through and taking a look at teasing things apart, we've got a procedure we call trend analyses. That's nice, right? For our ordered means, like our depression example, we probably have some idea of how those scores should change over time, right? We should see a linear trend of these scores over time. Trend analysis is a way to test whether or not we have evidence of a linear trend, potentially a quadratic trend. Things beyond that get kind of crazy. We don't often use those. But with ordered means, we can go through and use this. We can also use our linear contrasts, our plane comparisons. We can go post hoc testing types of procedures. I want to stay away from that to the greatest extent possible, but they're there for us to use. So how we go through and choose and our approach going to depend on our hypotheses, our conceptual considerations, right? Like what types of violations have we made? What types of things are we willing to assume and not assume? What type of study do we have? How many effects are we interested in teasing apart? All of these things are going to go into your approach for looking at different designs, okay? I'm going to tell you right now, Howell's chapter on repeated measures is excellent. It's thick, but it's not as thick as some of this stuff. Like, Alex asked Sean for a methods textbook to go through if you want to read a bunch of matrix algebra and summation notations and things along those lines, right? Howell is infinitely more accessible than some of that. Does a nice job of working through a number of different designs. Lauren, for your thesis, would definitely take a close read of that. If you have questions, come ask me. I'll help you sort of tease some of that apart. But a lot of the stuff that we're doing here is pulled straight out of Howell. Okay? So remember, when we're doing multiple comparisons, we've got some things we want to take into account, particularly the problem of committing, or the probability of committing a type 1 error. Okay? Our per comparison error rate is our probability of committing type 1 error on any given test, right? We set this as our alpha, right? We say alpha 0.05. I am comfortable with a 5% opportunity of me making a type 1 error. That is me saying that there's a difference when in fact there isn't a difference in the population, right? But if we're taking a look at family-wise error, right? This is the probability of comparing of making at least one type 1 error across a set of or series of comparisons, right? Calculate family-wise error as 1 minus alpha to the C power, C being the number of comparisons we're making. So, in as an example for 4 comparisons, our family-wise error rate is 0.185, which is nuts, right? Because this is saying like that I have, assuming that there are all of my 4 effects are actually null, I have about close to a 20% chance of saying that at least one of those are statistically significant when it's not in the population, right? So this is something that starts to accumulate quite quickly. And so our family-wise error rate is going to be bounded by alpha and number of comparisons by our alpha rate, but these two values are generally going to be fairly close with one another. So when we're thinking about our follow-up tests, we want to be very selective in how we're going about this stuff. We only want to take a look at things that are meaningful, right? If I go through and I think about what that graph looked like in the depression example, do I need to test whether or not time 2 differs than time 4? No. It's obviously going to be different. I got 400 goddamn people in this, right? I could have a very small difference that would come up as statistically reliable, it's nonsense for me to just start running pairwise comparisons just so I can write p less than 0.001 1,000 times, right? I don't need a statistical test that I can look at that. And if I know enough about statistics, I'm like, yeah, it's clearly going to be different, right? It's a 15-point reduction in the PDI on a repeated measure with 400 people. Yeah, that's going to be reliable, right? So making sure that your comparisons are meaningful, testing all possible comparisons is going to be complicated for the only reason that you then have to explain why, what's going on with 15 pairwise comparisons. Okay? In your problem sets, I'll have you like report on why four different pairwise comparisons. That's a hassle, right? And then you have to explain what's going on with those 4, right? If you go through and you have 5 different repeated measures and want to look at all possible comparisons between all 5 of those things, that's a lot, right? And it's going to be a hassle to go through and explain all that stuff. And you're going to get, this is the big thing, you're going to get weird stuff that comes up that now you're obligated to explain because you went through and tested it, right? I have no clue why these 2 things should be different. They shouldn't. It's probably a type 1 error, but, or I don't know. But I've gone through and I've tested it and it's there, so now Josh Clapp, the reviewer, wants you to tell me why it's different, because apparently it was important enough to test. So you get to spend time telling me why that's meaningful and different. Okay, keeping your analyses to a minimal number of fairly sort of meaningful theoretical tests is going to be your best approach. Okay, and so even if you're going through, even if you have a small number of comparisons, what you want to choose is a method of testing these and controlling for type 1 error that's sort of reasonable, that you could stand next to and say, okay, these are the tests that I did, recognizing that there's the possibility for inflated type 1 error, considering aspects of the design, sample size, things along those lines. This is my approach to going through. Maybe I control, maybe I don't. You just need to be able to provide a good justification for whatever it is that you chose to do. Okay, so have a good reason for going through comparing the stuff that you're comparing. What makes this so hard is that there's no right way to do this, right? There's a way that you might have been taught in graduate statistics, but there are like 7 different ways that you could go about that. Many of them are going to be equally defensible, right? This is where you lay out your legal argument for why we did what we did, understanding the statistics we're using, the design that we're using, the research questions that we have, so that you can put together a strong and solid justification for why you went about probing things the way that you did, right? There's 10 different ways to go through and run tests. There's different formulas that you can use. I can't say this is the way you do it all the time, or always do it this way and you'll be safe. There's a lot of different ways to do it. So what we're going to do is we're going to go through a couple of different things, talk about the issues that go along with deciding how to take an approach to making some of these tests, and then hopefully you'll be able to sit down with your own projects and say, okay, well, given these things, this looks like a reasonable approach. This is how I'm going to do, and I can stand next to this in a defense meeting or stand up to a review and say, well, this is the way I did it. Right? There are other ways to do it. This is the way I did it, and sort of this way would be fine, or this way would not be appropriate, given X, Y, or Z. But it makes it real hard. I wish that I could say, like, this is the way to do this all the time, but there isn't one way to do it. There's a lot, which starts to become kind of complicated. Okay. All right. Let me do this last slide. So a priori comparisons, small number of meaningful comparisons, right? Sometimes we correct using Bonferroni or Dunn-Siddick, right? Something that if we've got maybe 3 or 4 a priori comparisons that we've made, we still have some concern about possible type 1 error. We might go through and correct for this, but the idea is that by convention we don't have to. We're not obligated to correct for these because we called our shots beforehand, right? We said before we even collected the data, Lauren said, these are the things that I'm expecting to do, these are the contrasts that are important and meaningful, and so I'm going to test these as just what I'm going to do, right? Now, if we're doing post hoc stuff, this often is exploratory. After we've seen the data, we're like, oh, those 2 things look different, let me test those things, right? That's horribly increasing the likelihood of type 1 error, right? SPSS will give these readily to you, but again, you just don't want to indiscriminately print these off and put these in a publication, because then you look like a jerk. When I'm like, none of this stuff makes sense. You got twice as many figures as you do, because it's just measuring 1 and 2 and then 2 and 1. You didn't know what you were doing on this, right? You lose credibility with this, and then again, what ends up happening is if you're appropriately correcting for all possible comparisons with a post hoc, what you're going to do is you're going to give yourself a huge penalty if you're doing this appropriately to run comparisons that you don't care about and want to talk about anyway, right? So again, limited set of planned operatorial comparisons are going to be your best approach. If you're going to look through all possible pairwise comparisons, if this is truly exploratory in nature, you want to go through and look at just, hey, we need to just figure out what's going on. You need to have a strong rationale for why we would go through and look at all possible combinations, particularly with these repeated measures designs, because as soon as we get into mixed factorial stuff, you're going to have between, maybe multiple between, you have within. There's a whole lot of different things that you can go through and tease apart, right? And if you're going to appropriately correct for all of them, you have your criteria would be like p equals 0.0002 before anything ever comes up, because I'm running 40 different pairwise comparisons. So want to think very carefully when we get into this, have a game plan for how we're going to go about doing our follow-up tests, and having that plan be based on theory and a priori hypotheses about what about this is interesting and what do I want to tease apart. Okay. All right, folks. Thank you.